welcome everybody. Imagine you're a student and you've spent the better part of the last 2 semesters building your aerospace project. Now you're quite fed up with it and you need a way to get it away from you as quick as possible, as far as possible. What better than using a balloon or even a rocket? Exactly for this, there's REXUS and BEXUS. And if you're wondering who is crazy enough to travel to the high north, freezing their fingers off, setting it all up, well, just talk to Panic and Seth and give them a warm round of applause.
So welcome to our talk on the REXUS and BEXUS project, which is one way to get your student experiments into space, or if you're a teacher, you can propose a topic for your students to do so. We both are simple students from Jena and Munich, and we are not talking in the name of the REXUS and BEXUS program or the organizers. We just share our insights as participants in the program. So basically, REXUS and BEXUS is your flight ticket into space for an experiment that you designed. The program, REXUS and BEXUS, is realized under a bilateral agency agreement between the German Aerospace Center DLR and the Swedish National Space Board SNSB, which is somehow the counterpart, the Swedish of the German DLR. Furthermore, the Swedish share of the payload has been made accessible to teams from ESA, and also there are a lot of organizations involved in this project that support the teams in the design and development of their experiments. So first, for the REXUS, REXUS stands for Rocket Experiments for University Students, and it's basically a cheap launch system with 2 launches per year. These are formerly, so these rocket motors are formerly military rockets, surface-to-air rockets, that are repurposed to lift the scientific payload instead of warheads. Basically, these rockets can carry up to 5 experiments, and they are unguided rockets, so there's no active vector thrust control, for example, and they are simply spin stabilized. And the scientific payload mass is about 30 kilograms. So as you can see, there are several modules there, and basically normally there are 4 modules as these ring modules, and there may be one behind or below the nose cone. Then there's BEXUS. BEXUS experiments are simple balloon experiments, so atmospheric research balloons. You have a gondola where you can put your experiments inside. These are up to 6 experiments per balloon. And the plastic balloon is just filled with helium, and it then goes up to about 35 kilometers in height. And you have still communication during the flight with your experiments. So all these launches take place from Kiruna Space Center in northern Sweden, near a town called Kiruna. Just that you have a rough estimate where it is. So if you go there in summer, it looks like this. Basically, that's also one of the reasons to have the Space Center there. There's a lot of nothing. So if the payload and the motors fall back to ground, no one is hurt. And so it is a safe place to be. You also see in the foreground this big pad, the balloon pad. That's where the balloons are launched. And in the background, where you have, basically in the center of the image, there's the rocket launch pad. And there are multiple launchers there for different rocket types, because there are not only REXUS rockets launched there, but also other technology experiments. So how about all the organizations involved? So this table shows somehow a rough estimate of how these organizations work together. they bridge the borders to other services. So basically from the beginning on, there's the DLR space administration involved and SNSB involved as basically financial or providing the financial capital to just conduct the experiments and the flights and costs for travel and so on. So, and also, in this case, also ESA for the Swedish share. They are all involved in the project management, so they basically lay out how the project phases are, which dates to use, and so on. Then there comes a subcontractor, which is SARM, which is the Center of Applied Space Technology and Microgravity in Bremen. They have a drop tower facility where you can do microgravity experiments, and they are also involved in the REXUS and BEXUS program here. They basically are then advising all the teams throughout their project and are the direct partners to talk to if there are problems. The other organizations are, of course, still visible, so they are involved, for example, in the decision process, which experiment should be selected, but they are not directly involved, usually, in the design of the experiments. Then there's DLR Moraba, which is another part of DLR, namely the mobile rocket base. They are responsible for doing the launch together with SSC, the Swedish Space Corporation. SSC owns Esrange, for example. So they are providing all the necessary infrastructure for the launch itself, the rocket motors, and so on. So there are a couple of phases of the project, as I already mentioned. So first of all, the first step is the selection workshop. So you submitted a proposal to the REXUS and BEXUS committee, and they decide whether it looks interesting, what you're doing, whether it looks feasible with given time constraints or financial constraints. And if your experiment gets selected, there are several design reviews or reviews. These are usually at the end at the end of one part of the project to fulfill one milestone, and they are going with increasing granularity on just the details as your project evolves. So for example, at the preliminary design review, there are usually just the rough plan still, but not a final project yet and nothing tested yet, so to say. And so this just goes on until the bench test, for example, which is one of the tests where all the experiments are connected together, and it's basically just a couple of months before the launch campaign. So I was involved in the FOFS experiment. We did fiber-optic vibration sensing on board such a rocket, which was REXUS18, which was also last year in summer. We were a bunch of students from the TU Munich, and basically the core team were 6 people, 1 PhD student, 4 ordinary undergraduate students, and 1 pupil. So the experiment involved some laser optics or lasers and fiber optic circuit design, software had to be written, and so on. So what did we want to do? So basically we used fiber optical sensors to do vibration sensing, and vibration sensing means effectively measuring acceleration. So how can you use a fiber to measure something? One of these possibilities is a so-called fiber-Bragg grating. A fiber-Bragg grating is in principle a normal fiber, but with the difference that it does not transmit all light from one end to the other, but it has an inscribed periodic change of the refractive index. So this you can see with these dishes inside the fiber. These basically make the fiber behave in a way that one specific wavelength that we call the Bragg wavelength is reflected to the input side, and of course on the transmission side you see an absorption line. So that alone would not allow us to measure anything. But this Bragg wavelength depends on the temperature, for example. So if we increase the temperature by 1 Kelvin, we see a shift in the peak wavelength of this Bragg wavelength by 10 picometers. And the same way, if you take a 1 meter long fiber and expand it to by 1 micrometer, you see also a shift in 1 picometer of the wavelength. So this way, we can, for example, attach a seismic mass to the fiber, and if some force acts on the mass, we see an extension of the fiber. So we see a shift in the wavelength, and if we follow the shift in the wavelength, we can calculate the acceleration on this mass. So what are benefits of this technology for space? So first of all, these allow to build quite lightweight sensor systems. If you compare that, for example, to normal resistive strain gauges, we don't need isolation on the cables because this is just a fiber and we don't have any interference or electromagnetic compatibility issues with other electronics around. Also, there are no sparks, so we can place it quite close to propellants, for example, or we could think of a fiber that we just put on the complete rocket and have also multiple sensors inside this fiber. And we don't get any issues with the present parts that are around this. So there already exist studies and papers on how to use fiber optics or fiber Bragg ratings for space applications, but these are mainly lab setups, so these are not tested in flight. And there are only a few examples where this was done. So we thought whether it is possible to operate such an FPG, fiber Bragg rating measurement system, on a rocket, and just see how it turned out. So these were our fiber optical sensors. So the first one is the acceleration sensor. This one is a sensor that we bought. We also developed our own one, but we couldn't use it in the end, so we need to use the fallback solution. The overload capability is plus minus 50 G, which is important, but you will see later. Normally the rockets, so there's a REXUS manual that has several specifications on the rocket, and it says that the expected maximum acceleration is about 20 or 25 G. So this should be sufficient, we thought. Then we also have one fiber optical temperature sensor that you can see here, and there's also attached nearby the reference sensor. For the accelerometer, we also need a reference sensor, which was a normal MEMS-based electrical sensor that was placed close to the fiber optical sensors, and a lot of other temperature sensors around the module. So how does such an optical system with these fiber Bragg ratings work? So first of all, we have a light source that produces a very wide band of, or broad band of infrared light. This was done by a normal pump laser and an erbium-doped fiber. So then this very broad light goes through a fiber coupler and is split up into 3 beams that then go to each of our 3 sensors. So 2 accelerometers, fiber optical ones, and 1 temperature sensor. So from there, it goes through a 50-50 coupler and to the sensor. From there, the light gets reflected and goes back through the coupler and comes to a so-called interrogator chip. The interrogator chip basically measures in the first path. It has an edge filter in front of the light and a diode. And so we can measure the photocurrent of the diode, and we know basically that the peak wavelength of the Bragg rating. because also the light source might have some fluctuations in the intensity of light that it produces, we also need a reference of the total emitted light that we received. So we also have one path without the edge filter to have an absolute number, what was the input light basically for our sensor. So this is such a REXUS rocket. The rocket is about 6 meters long. Our experiment was directly under the nose cone, or below the nose cone, not within the nose cone. The nose cone was empty. And below us, there were 3 other experiments. There was, for example, Medusa from the University of Rostock, Strassat R2 from the University of Strathclyde, and an experiment called ISAC from KTH Stockholm. As you can see, there are some silver parts on it, so these are hatches, because all these 3 experiments had so-called free-falling units. These are ejectables that you can eject from the rocket that then fly down the normal way. So these are, for example, they can be used to test CubeSats, which was the case for Strassat. Therefore, you have these 10 to 10 centimeter hatches for Strassat. Then there's the rocket service module, that's from Morava, and the recovery module, that's also from Morava. So every experiment gets several interfaces, for example, power, for example, a data downlink provided from the service module, and the data is then transmitted by the service module to the ground station. And then below the recovery module, there's the improved Orion motor. So how did our experiment look like? As you can see, it is basically just this module with 356 millimeters in diameter. And we have a power supply there, and we have the light source, as I said. And from there, the light goes to the fiber couplers through this beam splitter. So you can see that there are 3 couplers, and basically the black part below the orange fiber cables that are rode up there below is the one of the 1 to 3 splitters, and then we get 3 output signals. So from each of the fiber couplers, we go one goes to the temperature sensor, and the other 2 go to the accelerometers. And from there, it goes back to the fiber couplers, and one way goes, of course, back to the light source, but we ignore that, and the other part goes to the interrogator chips. From there, it goes onto PCBs, through several filter stages, and to a microcontroller that then stores all the data on an SD card, and also transmits part of it down to the ground station. So that's this onboard data handling part. So how does such a launch look like?
8, 7, 6, 5, 4, 3, 2, 1, 0, 1, 2.
This is the view from the so-called science center. So there are basically 2 locations where you can be during such a rocket launch, because there are, of course, safety regulations there. So one is the science center, which this recording comes from, which is about 1 kilometer away from the launch site. And then there's the so-called radar hill, which is about 2 or a bit more kilometers away. And as you can see, basically from the science center, so you don't see that much. But we also had other experiments on the rocket. So they also had a camera on board the rocket, and we can also see the view from inside the rocket to the outside. So first of all, the rocket that you see there is not our rocket that is flying. That was just another empty rocket that was placed there, that's normally below the tower, and they just moved away the tower a bit. So the sound in the end, you probably noticed it, stopped. So first of all, you notice the spinning, which is at a rate of about 4 Hertz. That's just to stabilize the rocket during the flight, because, as I said, it is unguided. Then you probably noticed that we were above the clouds after about 7 seconds. And the other thing you noticed is the sound that somehow probably sounded, you probably don't know where it comes from. It's just the air that flows out of the modules because of the lower pressure outside. So that's basically the sound that you can hear. And in the end, you also hear that there was, the sound disappeared. That's because there was not enough air anymore for the microphone to work. And then we have a third one. This is so this was done by Muraba, and so it goes. So that was another rocket, but they mounted a camera on top the rocket launcher, and just see how it goes. So it goes quite fast. So we had, so now to our results, we first had the temperature measurements, and you can see that there's some spike from the fiber. So the first thing is both measurements are quite close together, so the sensing is correct, we can say. The other thing is that we notice is that at basically lift-off time, t plus 0 seconds, we have a spike from the fiber-optical sensor, which is basically because the fiber acts as an accelerometer in this case, because there's still a small mass attached to the fiber, but still it's a mass, so we can measure, or we can see the acceleration inside this temperature profile. The other part is that we have the acceleration from our normal sensor and the fiber-optical sensor, and we see that something bad happened. So at the beginning, everything seems still fine, but then at liftoff, something changes. So what has happened? That was the flight direction, so the z-axis. And basically 60 milliseconds before we get the official liftoff signal, that's the time between ignition and the rocket moves, basically, we see a very high acceleration that exceeds our breakdown force for our accelerometers, the fiber-optical ones. And basically the sensor could not reset into the old position, so some parts inside were damaged, and so we had an offset of minus 20 G around. But still, there was some signal, and we can adjust it by rescaling and adjusting the offset of the fiber back to the normal profile, so we can see that we reached about 30 G of acceleration. Of course, this is outside the spec of the accelerometer, so these are not fully trustable values, but that just shows that there's quite some energy at the start, at least, that exceeds the normally measured acceleration values. So the outcome was that, on the one hand, we can operate such a fiber-Bragg grating-based measurement system on this rocket, but on the other hand, there are still some problems that need to be solved or need to be avoided in the future that have to do with issues that you normally don't see if you sample too slow, that you can see these very high accelerations at the beginning.
Okay, so now I will talk about the ARCA team. We were a team of, was quite a small team of 5 engineering students from Jena in the eastern part of Germany. And the basic idea behind ARCA was that we wanted to build an ADS-B receiver to place it, for example, in a satellite, because in densely populated area, for example, at the Atlantic or so, there's no really control of the aircraft which are flying there. And the idea was that we wanted to build a small receiver which can operate, for example, at a satellite. And the goal was that we receive these ADS-B data which are transmitted from airplanes every second, nearly every second, during a BEXUS flight, and wanted to test the experiment during the flight. And we chose the BEXUS flight because we had much more longer time where we can measure these airplanes. And one other question was, we are in pretty height of 30 kilometers or so, so from which distance can we receive any airplanes anymore? So that's a very rough overview of the ARCA experiment. So we have our airplanes which are transmitting these ADS-B signals every second, and then we have the ARCA experiment which receives these data. We are saving the data on board. And then there's a E-Link, or so-called E-Link module in the BEXUS balloon, and we can transmit the data back to Earth and see it in the ground station and also save the data there. Here's another topic. We have our ADS-B data which are coming from the outside, and we have at the outside of our gondola we have the antenna mounted, and then we have the ADS-B receiver which is in our module. And we have an FPGA where we do all the signal processing stuff and decoding the frames which are coming from the airplanes. And then we have a small ARM computer which saves the data and also downlinks the data down to Earth. And also we could talk to the experiment and set some commands during the flight. The electrical concept is relatively simple. We have an RF receiver. The data is sent at a frequency of around 1.1 gigahertz. So we are filtering the data, we have an amplification stage, then we have a few other filters and amplifiers, and then we have a logarithmic detector, and the data from the logarithmic detector directly is input in an ADC, analog to digital converter, and then we are doing the signal processing stuff in the FPGA. And the FPGA sends the decoded data via a serial connection to the ARM computer where we can save it and store the data. And we had an Ethernet connection because this E-Link is mainly a Wi-Fi connection, something like that. It has a little bit more power than a Wi-Fi connection, but basically it's a Wi-Fi connection. We had some problems with the front end. We used on the first prototype, we used the so-called mini RDSB. You can take a look at the internet, it's well documented. And the problem was that there was only one amplifier and it oscillates a lot. So we split the amplification into 2 stages, and then we had no problems with amplification and so on. And you can see here that's our second prototype, and there the amplification is put into 2 stages. We built a baseboard, or a so-called baseboard. We had an FPGA underneath it, and the baseboard contains the RF receiver. You can see it here. You can see here the ADC, the analog to digital converter, and that's our ARM computer, which was also developed by us, and it was stacked on top of that. The board computer was developed by Hannes. He's one of our team members during his master thesis, and it runs Linux, and is, it was designed for low power consumption, so it also fits in our concept that we wanted to build a receiver which consumes basically nothing, or not really a lot of energy. You can see here a chart where we put all together. So in total we had a power consumption less than 1 watt. So we think that's quite okay. But for example, if we would use the experiment during a satellite flight, then the Ethernet connection wouldn't be needed anymore, so the power consumption could be reduced further, because the Ethernet connection consumes the most energy in the whole experiment. Mechanical, we built quite a simple mechanical or metal box. You can see it here in the left, where you have the connectors outside. From the left, there's the RF connector where the antenna is mounted. Then we have the power connection, and on the right we have the Ethernet connection, and 3 LEDs where we could see some indicators or some errors, for example, when the experiment was mounted in the gondola. A look inside of the box, it was really only this metal box, and we had here our baseboard, our ARM computer, and that's the RF connection which goes directly in the front. And here we had an ESD material only for isolation and thermal isolation of during the flight. In October last year, the experiment was started from Esrange. You saw some pictures before. At 10:51, we reached the floating level of around 28 kilometers, but we had a lot of, we had a strong horizontal winds, so the balloon had to be cut down at 12 o'clock. The problem is that they are not allowed to fly in the Russian sector. So we landed, or later we landed then in Finland, and it was good luck that we landed there. That's a picture of our gondola. You can see here, that was our small experiment. That's the power box where the batteries are located inside. And that's the so-called E-Link module, which is basically a Wi-Fi connection. And that was another experiment from, I think, Bologna, I5. They had done some meteorological measurements in the atmosphere during the floating phase. To the results, basically the experiment worked very well. We could track a lot of airplanes during the flight, and in total we received around 200,000 Mode S messages. And in total, that are around 110 unique airplanes we could see. And the maximum distance was around 620 kilometers. But we expected more. We expected a distance from around 1,100 kilometers. And the problem was that we had some dropouts with in our RF link. So we think that we had a broken antenna connection, which was mostly or likely due to a mechanical problem due to transport or so. Here's a picture during the flight. Here you can see that was the airplane which was from the highest distance, 620 kilometers around. And that's here in the middle, that's Kiruna and also Kiruna Airport. In blue, we have the valid Mode S messages we received during the flight. And at this time, we had the launch, and the count of Mode S messages increases a lot. And then we had this degradation you can see during the flight, and we think that that's the reason because of the broken antenna connection. So from time to time, we had a lot of messages we received, and then, for example, for 2 minutes, the count of messages dropped out completely, or nearly completely, so we had really problems with our antenna. But all in all, we received a lot of airplanes, and we could say, okay, the experiment is working well, actually. Thermal behavior, we mounted 6 ECREAT-C sensors in the experiment to monitor the temperature. And at the launch pad, or during the experiment, when it was on the launch pad, the temperature rises. And then, of course, the balloon was rising, and the temperature was rising until around, it was the outside temperature at minus 40 degrees. And then the gondola was moving slowly into the sun, and then the sun was shining directly on our experiment, so the temperature rises again. Okay, so we made a short time-lapse movie. Sorry, I have no real movie of the launch, and nobody in the team had a movie of the balloon start, but we made a short time-lapse where you can see here in the right, the yellow car, that's Hercules. Hercules is the launch vehicle at Esrange. You can see the gondola, which is mounted there, and the balloon is on the left. Okay, after the flight, we played all the data we received and made a small time-lapse movie where you can see the airplanes flying around Sweden and Norway. The interesting thing is, for example, to show you only one thing is, for example, you have here Kiruna airport, and you see airplanes which are flying to Kiruna, land and fly again. And of course, you can see a lot of airplane routes or streets in the air, which we could track during the whole flight. Okay, if you want to build an experiment and you want to participate in the REXUS BEXUS program, you maybe ask yourself now, how could I do that? And we think the first idea is that you have to get an idea, and we have only written some questions down. For example, was the experiment in similar kind already flown? Can we improve the early experiment which was flown some years ago or so again? And do you need external support which is critical for your experiment? For example, do you need any labs which cannot be provided by the REXUS BEXUS program, or do you need extra finance support, and so on and so on? And we think that in the first hand, it's important that you find people who are motivated to work in this project. For example, BEXUS projects are running for around 10 or 11 months, whereas REXUS programs are running for 12 months, no, 18 months. So that's a lot of time, and you have to do it mostly all during your study at university. So you also need people who are motivated. That's a very important thing in the REXUS BEXUS program, and we can say from previous REXUS BEXUS experiments, mostly the problem is that people lost the team or left the team, and the team had a lot of problems with the workload which has to be done until the launch campaign. So the next possibility to write a call for proposal, or to write a paper for the selection workshop opened in summer 2016. And for German students, you must not, but you should write a letter of intent until the beginning of August next year. And for European students, they should register at the ESA Education Project Database and write down that they want to participate in the program. And for details, you should see at rexusbexus.net because there's everything listed and you can read it later. Okay, some acknowledgements. We have the first team that were the team members of the first team, ARCA. We were this team. Thanks to the guys who brought us these images and so on, and the videos you saw, for example, from the REXUS rocket, were from the Isaac experiment and from DLR Morava. And if you want to read a little bit more, we have some web pages written down. And if you have questions or so, talk to us later or write us an email. Do we have some time left? 5 minutes 15. Sollen wir noch ein paar Fotos zeigen? Ja. Willst du?
Yes.
Okay, ja.
So we can show just a few images from the campaign, and then we do a Q&A. So this is the team photo of the REXUS 15 and 16 teams that were there. So you see these are quite a lot of people involved. And these were only the people that were sent to the launch campaign. There may be, or there are even more people involved in the project itself. And this is, again, the photo, but for BEXUS 18 and 19. So again, a lot of people. Yeah. Maybe we can open for Q&A now.
Thank you very much for this talk. Please give them a warm round of applause. If you have any questions, please line up at the 4 microphones we have here. And while you're doing this, off to the Signal Angel relaying a question from IRC.
We currently have a question regarding funding and regarding the costs involved with launches. Can you maybe elaborate a bit on the costs for launching with REXUS or BEXUS, maybe as cost per kilogram or so, and the total funding for such a launch?
So I don't know the total funding, but the launch itself is free. So that's paid by the REXUS BEXUS, so that's free for the teams. Basically what the teams have to pay, the teams also get some money, for example, to build the modules and some specific parts that are built, for example, by ZARM or by other companies where you just buy these things. And everything that exceeds that amount, I don't have an exact figure, a couple of €1,000, that then has to be paid by your own, or you have to develop it by your own, or you need a lab of your university or some machines of your university. So there you can just see where you can get other support or other sponsors for these parts.
A question from the front right microphone.
Okay. Okay. Hello. I have a question regarding the fiber-optic measurements you did, because you explained that it has some advantages, for example, that it can be built very lightweight. Now my question is, did your experiments or do you hope that your experiment will have some effect on the development of these measurement systems for actual missions from NASA or the DLR, for example, some kind of fiber optic measurements being done on ISS? So what lies in the future?
So I don't know of any specific plans or things, but so we see that there are some problems with the fiber optics, but in total, due to that you don't need no isolation from of the fibers compared to electrical cables, so that there might be some programs, but nothing specific that I know of.
Can I ask a follow-up question, a short one?
Yes.
Can you give a rough estimate on how much weight you can save in comparison to the models used currently for measurements?
Not by heart, sorry.
Okay, thank you.
Front left microphone.
Hi, thanks for the talk. I'm interested in some numbers for both REXUS and BEXUS. What's the kind of flight duration you can achieve, and what about the maximum altitude?
Yeah, so the altitude, I think we had that on the slide, is for the REXUS rockets about 80 or 70 to 90 kilometers. So it depends, of course, on the mass of the rocket. And usually you try to get all the experiments that started for this rocket also on the rocket, that you don't have to fly an empty experiment. So therefore you probably just take away some of the height and take the heavier experiment. But so our flight, because all our modules were quite heavy, our flight was only up to 80.7 kilometers. But our sister flight, REXUS18, was to 86 or 87 kilometers.
A question from our signal angel on IRC.
Somebody wanted to know what happens to the rocket when it reaches its high point, the highest altitude. Does it come back? Can some parts be reused? Things like that?
Yes, so the 80 kilometers are not sufficient to get the experiments into orbit. So basically everything falls down again. There will be, or usually there's a motor separation. So the motor falls down before the payload, and then sometime later the payload comes down again. This is so that the payload falls back on a parachute, and you can see that here how it looks like after these couple of slides. So that's just the payload without the motor. That's how it is mounted on the launcher, and that's basically how it how REXUS18 came back.
Front left microphone.
I think you missed some of my question. I also wanted to know about the flight duration of REXUS and BEXUS as well.
So the REXUS flight, these are 3 minutes up, and then probably about, I think, 8 minutes or so down. But most of the time is on the parachute, so there's nothing special anymore happening.
BEXUS is a little bit complicated to say. So, for example, our flight was only around 2 hours or so. But for example, one of the last BEXUS flight, which fly this year, in October this year, they had a very long flight because there were no horizontal winds. So there are pictures where the balloon was launched 2 hours ago, and they could take a photo from the launch pad where the balloon was visible in 30 kilometers height. So it could be quite long, and it depends on the horizontal winds, for example, and also on the constraints of the experiments. Some experiments want to have a long duration of measurement, and some experiments want to have a slower duration of flight or of floating, because, for example, they only want to take measurements in the rising and falling of the balloon.
Are there any more questions? It does not look like that. So please give a warm round of applause to Panic and Seth.